Right now, electricity is being generated to power the light you're reading by. Not stored, generated, this very second. The global power grid serves billions of people across hundreds of thousands of kilometers of wire at a frequency that must stay within 0.5% of exactly 50 or 60 hertz, depending on where you live, or the whole system fails. And almost none of it can be stored. That last fact is stranger than it sounds. We'll come back to it. Why can't we just save it for later? In 1882, Thomas Edison switched on the first commercial power station in New York City. It served 59 customers, direct current, coal-fired. Within a decade, Nikola Tesla and George Westinghouse had won the so-called War of Currents. Alternating current became the standard, and it has stayed the standard ever since. By the 1960s, regional grids were interconnected into the vast national networks we rely on today. And through all of that, every upgrade, every innovation, every gigawatt added, one fundamental constraint never changed. The grid was built on one core assumption: electricity must be consumed the instant it is produced. Generation and demand must match, continuously, in real time, at scale. That assumption shapes everything about how the modern grid works. So what is actually happening inside the power grid? At its core, the grid is a machine for moving electrons from where power is made to where power is needed instantly. But between the generator and your outlet, 5 distinct stages are doing very specific jobs. Stage 1. Generation. Spinning turbines, coal, gas, nuclear, hydro, convert mechanical energy into electricity. Stage 2. Transmission. High voltage lines carry that power hundreds of kilometers with minimal loss. Stage 3. Transformation. Substations step the voltage up and then back down for safe local delivery. Stage 4. Distribution. Neighborhood lines carry lower voltage power to streets and buildings. Stage 5. Consumption. Every switch you flip adds or removes load, instantly. Together, these 5 stages form what engineers call the alternating current grid, a system that must balance supply and demand at every single moment. Here's what makes the grid so unlike any other energy system. Every large generator connected to the grid is physically spinning. In North America, they spin at exactly 60 revolutions per second, 3,600 revolutions per minute. In Europe, most of Asia, and Australia, 50 revolutions per second. That rotation produces alternating current, voltage that rises and falls 60 times every second. Now here's the critical part. Every generator on the grid must spin in perfect synchrony with every other generator. If demand suddenly drops, because a big factory switches off, generators have more energy going in than coming out. They spin up. Frequency rises above 60 hertz. If demand suddenly spikes, generators slow down. Frequency drops. At 59.5 hertz, automatic systems begin shedding load. At 59 hertz, power plants start disconnecting to protect themselves. The entire grid operates within a band less than 1 hertz wide, continuously. This is why storage isn't just a convenience. It's the missing shock absorber the grid never had. So why can't we just store the electricity itself? The honest answer is, you mostly can't. Electricity is electrons in motion. A capacitor can hold a charge, but nowhere near enough for grid scale. The total energy stored in all the utility-scale batteries in the United States today is enough to power the country for approximately 20 minutes. 20 minutes. This isn't a failure of effort. Billions of dollars have been spent on battery research. It reflects a fundamental physical reality. Chemical fuels store roughly 50 to 100 times more energy per kilogram than typical lithium-ion batteries available today. The grid doesn't store electricity directly. What it stores, when it stores anything, is energy in a different form. And every conversion loses some along the way. That loss is called round-trip efficiency. There is one storage technology that actually powers the modern grid at scale. It doesn't use lithium. It uses water and gravity. When the grid has surplus electricity, typically overnight, pumps push water from a lower reservoir to a higher one. When demand peaks, that water flows back down through turbines. Right now, pumped hydro accounts for around 93% of all utility-scale energy storage on Earth. Not batteries, not flywheels, not hydrogen. Water pumped uphill. Solar panels created a problem nobody expected. Australia has more rooftop solar per household than any country on Earth. And that created what engineers call the duck curve. Demand dips in the middle of the day, then spikes sharply when the sun goes down and people come home. Add solar, and the midday dip deepens. Every other source has to ramp up fast the moment solar output drops. The steeper that tail becomes, the harder the grid is to manage, and the more urgent the need for storage to bridge that gap. Utility-scale battery storage is growing fast, but perspective matters. Today's largest grid-scale batteries store thousands of megawatt-hours. Entire facilities the size of city blocks, rows of shipping containers packed with cells. Tokyo's peak grid demand reaches around 50,000 megawatts. Even the world's biggest battery farm can only supply that for a few minutes. That isn't a criticism. It's a calibration. Battery storage isn't designed to replace generation. It's designed to shift a few hours of solar generation into the evening, to blunt the duck curve, to smooth the frequency, to buy time. Batteries respond to grid frequency changes in under 200 milliseconds, faster than any power plant can spin up. That speed is what makes them valuable, not duration, speed. The gap that remains is long-duration storage, days to weeks. It's largely unsolved. Hydrogen is the most discussed option. Use surplus electricity to split water, store the hydrogen, burn it in a turbine, or run it through a fuel cell when needed. The problem, round-trip efficiency, is around 30 to 40%. You put in 100 units of electricity, you get back roughly 35. That's not disqualifying. Surplus solar that would otherwise be wasted is still worth capturing at 35%. But it means hydrogen will complement the grid, not replace its other needs. The search for the grid's missing battery is still very much underway. Back in Australia, the same country whose rooftop solar created the duck curve, one battery proved something else. To make this real, let's look at one specific installation: the Hornsdale Power Reserve in South Australia. Built in 2017 in 100 days, after Elon Musk bet on Twitter that Tesla could do it. He won the bet. In December 2017, a coal plant in Victoria tripped unexpectedly. Grid frequency began dropping. The Hornsdale battery responded in 140 milliseconds. The competing gas peaker plant also contracted to respond. Took 4 seconds. That 140 millisecond response prevented what could have been a cascading blackout across South Australia. In its first 2 years of operation, Hornsdale saved the Australian grid an estimated 150 million Australian dollars in frequency control costs on an asset that cost 90 million to build. Generation, transmission, transformation, distribution, consumption. A system that must balance supply and demand to within 0.5% at every moment. 93% of all grid-scale storage on Earth is still just water pumped uphill. The best batteries in the world can power the US grid for around 20 minutes. And a 140 millisecond battery response in South Australia was fast enough to prevent a blackout that no power plant could have stopped. The grid isn't a primitive system waiting to be upgraded. It's one of the most precise, most interconnected, and most underappreciated engineering achievements in human history. The grid storage crisis is being pushed harder every year because of solar panels, millions of them added every month. But most people have no idea how a solar panel actually generates electricity from light. There's no combustion, no moving parts, no heat, just light hitting silicon. How solar panels actually work, next on NG Simple. Subscribe to NG Simple so you don't miss it.